At first glance, it looks like a simple load. Bundles of cane stacked high, carried along dusty roads by convoys of trucks that stretch to the horizon. But underneath this surface lies one of the most complex and underestimated operations in industrial agriculture: the safe, timely, and stable movement of more than 2 billion tons of sugarcane every year. What the eye sees as rustic and repetitive, engineering sees as a living current, a mass in motion, as reactive as any fluid under pressure. Sugarcane isn't just biomass. It's fiber saturated with water, tightly packed, breathing hot, and fermenting. Every stalk, every bundle, carries within it a biochemical clock that starts ticking the second it's cut. Transporting this material is not just about moving weight from field to mill. It's about managing a living flow, one that reacts to time, heat, and pressure. In technical terms, sugarcane behaves more like a semi-fluid composite than a solid. It shares characteristics with materials like slurry or pulp, dense, moist, and prone to internal transformation when compacted for too long. To understand the logistics of sugarcane, imagine a hydraulic excavator in a mining operation. Every scoop must be balanced, every load calibrated to avoid collapse or imbalance. The same principle applies here. When too much weight is forced into a trailer, especially without load segmentation, the bottom layers compress beyond recovery. Fermentation begins inside the mass, breaking down sucrose before the mill even has a chance to extract it. It's like losing the crop on the highway, molecule by molecule. This structural risk isn't theoretical. It happens silently, frequently, and invisibly, especially when fleet managers push for maximum load efficiency without understanding the thermodynamic consequences. A poorly distributed sugarcane load without proper airflow or spatial buffering can become a chemical incubator. The bottom overheats, pressure rises, and by the time it arrives at the mill, what was cane has begun turning into compost. The solution doesn't come from guesswork, it comes from engineering. Historical innovations in naval bulk transport offer key lessons. In ore carriers, for instance, the hold is divided into segmented compartments, not just for structural integrity, but to prevent internal heat pockets and compaction. This principle, once applied to minerals, is now re-emerging in agribusiness. Some of the most advanced sugarcane trailers are adopting modular designs that balance weight while preserving air pockets inside the load, drastically reducing thermal hotspots. Because sugarcane is not rock, it's not inert, it's not dead. It's a reactive material, dense with fiber and moisture, fighting to decompose the moment it's harvested. That's why the logistics chain treats it less like cargo and more like volatile energy mass in controlled fermentation. It's not just about moving cane, it's about controlling what happens inside it during the journey. This is where mechanics meets biology, where the logic of fluid dynamics crosses paths with agro-industrial precision, where every trailer becomes a chamber, every driver an operator of flow, and every minute a risk. There's a type of breakdown in sugarcane transport that leaves no visible trace. No shattered axle, no spilled cargo, no overturned trailer on a rural highway. Instead, it occurs molecule by molecule, in silence, as time eats away at value. From the moment a stalk is cut, the race begins. A race not against distance, but against cellular inversion, the natural chemical process that transforms sucrose into byproducts. The mill can no longer recover. In this race, delay is defeat. And in Brazil, one of the world's largest producers, more than 30% of sugarcane loads still spend over 5 hours waiting to be processed. This isn't just inefficiency, it's loss at scale. Every hour, enzymes inside the cane trigger sucrose degradation, converting sugar into compounds like glucose and fructose. The longer the wait, the greater the loss. But the most striking aspect of this problem is that it's often invisible to those managing the process. Because when logistics are based on distance, or tradition, or habit, they ignore the ticking clock inside the cane cells. The technological counterattack to this biological decay comes from predictive logistics. Today's most advanced sugar operations are turning to algorithms, systems that integrate weather forecasts, harvester telemetry, soil conditions, and traffic data to calculate in real time which truck should go where and when. These aren't generic routing apps. They're agro-intelligent platforms designed to move biomass under metabolic threat, and when implemented well, the results are immediate. One of the most surprising insights came from a logistics study conducted by UNESP, where researchers compared two dispatch strategies, one optimized by route distance and another optimized by time to crush. The result? The distance-optimized strategy, though seemingly efficient on paper, caused 17% more sucrose loss. Because a shorter path means nothing if it leads to a longer wait at the mill. The real enemy isn't the kilometer, it's the minute. In the fields of Mato Grosso, this knowledge became practice. A regional cooperative redesigned its harvest logistics network around dynamic routing. Harvesters, equipped with GPS and sensors, now communicate directly with a central system. As cutting begins, the software calculates the ideal dispatch moment and vehicle pairing to minimize cane age. The result? A 12% increase in TCH, tons of cane per hectare. Not because more cane was planted, but because less sugar was lost in motion. The conclusion is neither dramatic nor theoretical. It's purely operational. Sugarcane doesn't spoil because of traffic jams or road dust. It spoils because its journey is disconnected from the life it still carries within. And while most transport systems treat it like a passive product, reality insists otherwise. As one agronomist put it bluntly, cane is not late because of roads. It's late because the road doesn't read the clock inside the plant cell. Even when the journey is fast, sugarcane carries another invisible vulnerability: heat. Not from the sun, not from the engine, but from within. When stacked densely in trailers without ventilation, the cane begins to oxidize. The core of the load, cut off from airflow, traps humidity and microbial activity. Temperatures rise. Biochemical processes accelerate. And without warning, what began as fresh, high sucrose biomass becomes a thermogenic reactor, pushing internal heat beyond 50 degrees Celsius. This transformation doesn't happen in days. It happens in hours. In some cases, just 3. Inside these sealed chambers of fiber and moisture, microorganisms thrive, respiration increases, and with every degree of heat, more sugar is consumed, not by industry, but by decomposition. The load that left the field as sugar arrives at the mill as biomass waste. The cause? Not road quality, not mechanical failure, but air, or rather, its absence. To break this chain reaction, engineers turn to a concept long used in other crops: cross-ventilation. Modular bins equipped with vertical airflow channels, originally developed for onions and garlic, are now being adapted to sugarcane transport. These bins allow air to circulate from the bottom up, reducing internal temperature gradients and slowing the oxidative clock. The difference is measurable. In Pernambuco, controlled field trials tested these ventilated bins side by side with traditional trailers. The result? A 30% reduction in TRS loss. Total reducing sugars, the indicator of how much fermentable material remains, were significantly preserved, not by refrigeration, not by additives, but by air. In Colombia, a mill went one step further. It installed thermal sensors on its sugarcane transport fleet. Each truck now transmits internal temperature data to a central dashboard, allowing operations teams to track and intervene if heat rises beyond safe thresholds. Within 3 months, variability in TRS dropped from 18% to 5%. That single-digit difference means thousands of tons of sugar saved annually, not at the harvest, but in transit. The insight is simple, the implications profound. Every ton of sugarcane is in a state of chemical tension. With proper airflow, it remains cargo, rich, usable, full of value. Without it, it becomes compost, active, unstable, and lost to heat. The material doesn't choose its fate. The trailer design does. Because in this equation, the cane is never neutral. It's either sugar or gas. The air decides. If precision matters to you, check the pinned comment. It's a small detail, but like airflow, it changes everything. Cutting sugarcane is not the end of a process. It's the beginning of a reaction. A biochemical countdown starts the moment the blade slices through the stalk. Inside, plant cells rupture, enzymes activate, microbial populations, once dormant, awaken. The harvested cane begins to transform, not metaphorically, but chemically. And from that point forward, logistics becomes far more than movement. It becomes intervention, engineering, a race to preserve molecular integrity before it slips away in heat, oxidation, or time. The traditional image of agricultural transport, static trailers, patient loads, passive materials, doesn't apply here. Sugarcane is not patient. It respires, it ferments, it transforms under its own biological pressure. Unlike grain, which can remain dormant for months in a silo, cane behaves like a living tissue separated from its energy source. It begins to consume itself. And what the industry is slowly realizing is that the window to extract its true value is measured not in days, but in hours. This demands a total rethinking of how post-harvest operations are structured, because logistics, in the context of sugarcane, cannot be defined by kilometers alone. It must be defined by time, temperature, and biological volatility. The faster the system can recognize this, the more efficiently it can align harvesting, transport, and processing in a synchronized chain. Some regions have already begun treating sugarcane not as freight, but as reactive biomass. In Queensland, Australia, the Smart Cane initiative introduced a radical integration of harvesters and trucks through real-time sensor networks. It's not just that a truck is sent when a harvester finishes its row. It's that the harvester communicates cutting data, including yield estimates, cane variety, and environmental parameters, to a centralized dispatch system. This system cross-analyzes weather forecasts, road congestion, and mill capacity to determine precisely which truck should be sent, at what moment, and by what route, to minimize the biochemical age of the cane. In practice, that means every stalk spends less time fermenting and more time delivering usable sugar. This is not automation for automation's sake. It's precision logistics applied to living material. And it reflects a larger truth in modern agriculture, that engineering must now interact with biology in real time. Sensors are no longer just used to measure performance. They are used to protect molecular value. In this new model, data isn't abstract. It is the bridge between machinery and metabolism. On the ground, this shift reshapes the role of the field operator. Drivers are no longer simply navigating roads. They are navigating timelines, thermodynamics, moisture gradients. Their load is not stable. It is in flux. It breathes. It heats. It deteriorates if mistreated. This transforms the truck cabin into a control point, where routing decisions, trailer type, and loading density can define whether the cargo will be processed as sugar or downgraded as waste. Some operations now equip their fleets with thermal sensors, GPS-linked timers, and load history trackers. These tools allow managers to visualize a real-time heat map of their supply chain. If a trailer remains stationary too long, or if internal temperature begins to rise beyond safe thresholds, the system flags it. Action is taken. The route is altered. The processing order is reprioritized. Because every delay represents not just lost time, but lost chemistry. And this chemistry matters. A mere 5-degree increase in internal load temperature can accelerate sugar inversion by 40%. A delay of 1 hour can reduce TRS, total recoverable sugars, by several percentage points. Scale this across thousands of tons per day, and the economic loss becomes enormous. But what's more important is that it's avoidable, not through force, not through speed alone, but through orchestration. This orchestration is where post-harvest engineering becomes an art form, not in the romantic sense, but in the sense of precision, timing, and alignment. The sugarcane supply chain functions like a biological symphony. Every section must enter at the right time, in the right sequence, for the result to have value, and each machine, each human, each decision point plays a role in that rhythm. Because the truth is simple and the implications profound. The sugar is made in the field, during photosynthesis, growth, and ripening, but it is preserved or lost in the hours that follow, on the road, in the bin, in the wait before crushing. The logistics chain is not a conveyor belt. It is a preservation corridor, and its success depends not just on horsepower and infrastructure, but on understanding that every load is a race against biology. To recognize sugarcane transport as post-harvest engineering is to place logistics at the center of value retention. It is to respect the material, not as an object, but as a process. And it is to empower those who move it, the drivers, the dispatchers, the field coordinators, as agents of biochemical preservation. Because in the end, what they carry is not just weight, it is potential. And every kilometer counts, not just in distance, but in transformation. If you appreciate finding value where few are looking, the pinned comment holds something curated for that same mindset. It's brief, precise, and worth your attention.